So hopefully you were able to see a difference between dendrites, cell body, axon, and then synaptic terminals, or axon terminals. Those are the three main parts of the neuron. And now the neuron is what we're going to be focusing on for the next week. Then, once we understand how a neuron does what it does, we're going to then start to learn about where those neurons are placed in the rest of the nervous system and what they do. But I think it's best to look at it from the small point of view first and then slowly go bigger. So we left off on one of these images here, and we were talking about a very particular fat that's found on the outside of the axons. What is that substance on the faster traveling axons? It's a fatty substance and it covers some of those axons. Remember what we called it? Thank you, Daphne. Myelin. So myelin, remember, is an installation on the axon, and it allows an impulse, a transmission to travel faster through that neuron, specifically through the axon of that neuron, than it would without it. And in fact, if you look at brain tissue or spinal cord tissue, you can see where all of the myelinated axons are and where the unmyelinated axons are. The two different parts of the central nervous system tissue itself is usually classified as white matter, which contains all of our myelinated axon neurons. Remember, this is a cross-section of the spinal cord. It's a transverse plane, and you see all of these myelinated axons bound close together. Then you have gray matter, where you find unmyelinated, so there's no myelin on these axons. And this is also where we find the dendrites and the cell bodies of the neurons. So when you see white matter, we're just talking about those myelinated neurons. Same thing with the brain. The outside of the brain is known as gray matter. All of the faster traveling parts of the brain, which contain myelinated axons, are known as the white matter. You can see it here in an actual human brain sliced mid-sagittally section. You can see this is one half of the brain. Can't actually tell which half it is. You see all this white matter, white matter, white matter, and then the darker, grayer looking substance is the gray matter. So this is where all of our myelinated neurons are. Unmyelinated neurons, dendrites, cell bodies, and a few other things too. So let's actually write down these two differences: gray matter and white matter. First, white matter is just axons of those neurons with myelin. We can see again here, this is white matter. So these are all myelinated axons in this area of the brain. All myelinated axons. All of these connections are myelinated axons. These are all these neurons packed really tight together. This is spinal cord. So this is a section about right here. All this is the myelinated neurons. All this is the myelinated neurons. Well, then what exactly is in the gray matter? The other stuff. Well, the gray matter contains the cell bodies of the neurons. It contains those finger-like projections, the dendrites of the neurons. It contains axons without myelin. Remember, myelin is fatty, so it's going to have a white appearance to it. It's going to look whiter than the areas that don't have myelin. And then there's another cell that you guys came across in your article called neuroglia. You could pronounce it neuroglia or neuroglia. Either way is fine. Neuroglia is more of like the British-derived way of saying that word. Neuroglia is more of the Americanized version. A lot of scientific words have some different pronunciations sometimes because of who uses them more in what area of the world. So the white matter is the axons with the myelin. The gray matter are the cell bodies, the dendrites, the axons without the myelin, and the neuroglia. So most of the connections in our brain are on the outside, because this is where cell bodies touch dendrites, and dendrites touch some axons. And in fact, we have all these folds so that we can have more of those cell bodies and dendrites in a particular closed-in area. Then these are all the connections between all of those neurons in the brain. And there are millions of connections. And the connections are actually changing. When we learn things, we make new connections, physical connections between neurons. A dendrite attaches to another cell body, or a synaptic terminal attaches to the dendrite of another cell body. And that helps us remember something. It helps us be able to perform something. It's what the process of learning is, the reconnecting of neurons and connecting of neurons. So those are the two parts of the nervous system. But if we go down deep into the neuron itself, we then need to try to understand, how does a bit of information get from one end of the neuron to the other end of the neuron? And we call this an impulse, because it's electricity that's actually traveling down the axon through the neuron. And that charge is often referred to as an action potential. Anytime you're dealing with electronics, you usually use the word potential. It means that there's some potential of energy versus the lack of energy down here. And so we think of energy as some type of ability to do work. Electricity happens to be the movement of electrons. This type of electricity happens to be the movement of minerals. Potassium, which has a positive charge, sodium, which has a positive charge, and then a little bit of chlorine too. But by using these minerals, we can actually have an electric impulse travel down the neuron. Let me show you. So this is a cool simulation of a neuron. This is an axon, an unmyelinated axon. It's been sliced to expose the inside and then the membrane of that axon, that cell membrane. I'm going to stimulate the neuron, and I want you to notice a little electrical charge travel down that axon. And as it travels down the axon, it opens or closes these gates around that neuron's axon. I'm going to do it again. Watch the electrical charge travel down, and then as soon as that electrical charge, that potential, gets to a particular spot, it opens up gates, closes gates. And what that does is it changes the concentration of sodium and potassium inside the neuron versus outside the neuron. Let me show you. Now you can see electrical charges. When a neuron is just resting, when an impulse is not coming down, we have an overall positive charge. When it's resting inside the neuron, we have an overall negative charge. Think of a magnet. You have a positive charge on one side, negative charge on the other. I'm going to stimulate an impulse. So a message is going to travel down that neuron, and it flips the charge just for a moment so that we have a negative charge on the outside, positive charge on the inside. That will happen sequentially all the way down that neuron. So what you see here is happening all the way down, almost like a set of dominoes, until we get to see one of those dominoes fall in order to see the charges change. Now let's look at the different concentration of these minerals, and then we'll start taking some notes, because I know you're probably getting a little confused. So I'm going to stimulate the neuron. You'll see the potassium and the sodium levels change in order to flip the charge. Gotta wait for it to reset. Let's not do that. I'm gonna go slow motion. I'm gonna stimulate the neuron. Notice the potassium, sodium outside, potassium, sodium inside. Gets to the point, potassium numbers go down, sodium numbers now in response to that eventually go down. On the outside, your sodium numbers went up. Let's see that again. Let me just reset. As that charge travels, we get a difference in electrical charge right at our location. Then eventually that charge is going to get back to normal as the sodium and potassium ions go back to where they're supposed to be. This process allows for a neuron to carry information, electrical information. And we call this an action potential. So please write down transmitting impulses. We're going to take some notes on this. I'm going to show you some images, and then we'll go through that simulation again if we need. A neuron cell membrane at rest. So I want you to think of the neuron not being stimulated yet. When it is at rest, the outside of the cell membrane has a positive charge, and the inside of the cell membrane, remember we're talking about the axon, the inside of the cell membrane is negatively charged. So you have a positive charge on the outside, a negative charge on the inside. So we start with the negative on the inside. Oops, shoot. Negative on the inside, positive on the outside. We call this polarized. Higher concentration of sodium ions outside the cell membrane and a higher concentration of potassium ions inside the cell membrane causes us to have this cell membrane with an overly positive charge on the outside and negative charge on the inside. So even though these sodium and potassium, Na is the chemical name for sodium, K is the chemical name for potassium, sodium has a positive charge on its own. Potassium has a positive charge on its own. But if you have more positive charges on the outside compared to what's on the inside, you'll have an overall positive charge on the outside and a negative charge on the inside. You don't necessarily have to have negatively charged ions in order to get positive on the outside, negative on the inside. We have more of the sodiums on the outside when it's resting, polarized, than we do potassium ions on the inside. And this is going to be a very important thing as we watch this unfold. Now, what is keeping the membrane in this state? What is allowing there to be more sodium ions outside and less potassium ions inside is a very important cellular pump, which we call the sodium potassium exchange pump. Can anybody guess what that pump does? Look at its name. What does the sodium potassium exchange pump do in order to keep more sodium ions outside and less potassium ions inside? What's the signal it's sending? Okay, Daphne, exchanges sodium. Does it exchange anything else? Because it's a sodium potassium exchange pump. Oxygen potassium. So it exchanges sodium and potassium. What does a pump do? You ever seen a water pump? It takes water from one location and it moves it somewhere else, right? If we have instead of a water pump, exchange pump, we have a sodium potassium exchange pump. So we have sodiums that get exchanged with potassiums. And it allows the cell membrane to keep lots of sodium ions outside and then just a few potassium ions inside. And it's a very complex little cellular machine. Very important. It's going to become much more important as we move forward here. There are also protein channels that let potassium go in and out, but not sodium. So we have a sodium potassium exchange pump. So this is an active motorized pump that's exchanging potassium with sodium, potassium with sodium, potassium with sodium, putting the sodium outside the cell, potassium inside the cell. But we're able to maintain less potassium inside because potassium can just bleed in and out of that membrane. And so that sodium potassium pump's constantly pulling potassium back in and then pushing sodium out, constantly pushing potassium in, pushing sodium out, while these open channels just allow potassium in and out. But they don't allow sodium through. The only way sodium can get moved is if something very special happens to that membrane. Some potassium, that's the K+, it denotes that we're talking about potassium. It also tells us that it has a positive charge, just like the Na+ tells us we're dealing with sodium, which has a positive charge, diffuses out of the cell while negative ions remain inside. Therefore, we have what is called polarization. Polarization is the idea of having one area, one charge, the other area, the opposite charge. Inside the axon cell membrane, we have a negative charge. Outside the cell membrane, we have its opposite, which is a positive charge. So we say that it is polarized. You could almost think of it as a gun with the little cock pulled back. It's ready to fire. And let's take a look at a few of these images here so we get an idea of what I just went over in the notes. So here's a cell membrane, particularly a section of an axon cell membrane. Inside the axon is cytoplasm, and it has an overall negative charge. Remember, there's less potassium plus ions floating around than there is out here, where we have sodium plus and potassium plus ions. So we have an overall positive charge. There are these gates that allow potassium out and in if it wants to go. But sodium won't be able to come in through those gates. Here is your sodium potassium exchange pump. Not doing anything at the moment, sitting there in the cellular membrane. This is polarization. This is a resting neuron right here. Now, let's say a signal comes in the dendrite, moves through the cell body, gets to that axon. We start to see sodium ions now have the ability to flow into the cell membrane. These very special gates are going to open. Because we have this overall positive charge, sodium is going to fly. It's going to rush into that negatively charged area because opposite charges attract. That's going to create an overall area that has a negative charge, and it's going to move one section at a time, changing this charge from positive to negative, and then flooding the cell with sodium because these gates open, causing the overall inside to become positive. For just a moment, we depolarized the membrane. Then after that signal travels down, the negative is the signal. Think of electricity. It's a negatively charged phenomenon. We then, because there's so much positivity in here, we're then going to start to get some of those positive potassiums are going to start flowing out of the cell because there's just too much positive charge in here right now because all these positive sodiums flooded in. All those potassiums with the positive charge are going to then again create an overall positive charge out here. So now we have tons of potassium. We have a little bit of sodium out there, both with a highly positive charge. It's not back to resting state yet. We call this repolarization. It's not quite polarization. And then after the wave of repolarization passes, the sodium-potassium exchange pumps get the potassium outside, inside, and the sodium, which happens to be inside, back to the outside, creating that polarized neuron or the resting state neuron. We call this process an action potential. So we have a stimulus that gets applied. It could be something touches your skin. It could be something that originates from your brain. It could be something that stimulates a pain receptor. That's a stimulus. It's going to then stimulate the neuron by changing the concentration of sodium and potassium around that neuron. Gated channels open when the stimulus is applied and allow sodium to enter. And it floods in really fast. This results in what we call depolarization. The inside of the cell becomes now more positive than the outside of the cell. It has flipped the polarization upside down. We started polarized with positive on the outside, negative on the inside. We flip because all the sodium floods into this inside the cell, axon membrane, and then it creates an overall positive charge on the inside for just a little spot, and then a negative charge outside. The potassium then leaves the cell rapidly. Remember, it has those channels that it can just fly right through. And then the cell results back to its resting potential. The reason for this step is because once something stimulates your neuron and stops stimulating it, we don't want that signal to keep being stimulated over and over and over again. We want it to stimulate, send this message, and then stop, so that we have the ability to know when something is no longer touching us, to know when something that's hot isn't hot there anymore, or cold isn't cold there anymore, or whatever signal is being transmitted, Doesn't just kind of repeat. So the cell membrane has potassium rush out, which creates this similar state to the resting potential because it's positive on the outside, like we would see in resting, negative on the inside, but it's positive because of all this potassium that's out there. The sodium's inside the cell. It's not supposed to be there in resting state. And so we call this the repolarization. And it actually sends the cell membrane too much in the wrong direction. That's a good thing though, because it stops that neuron from firing multiple times accidentally. So once the signal goes down the neuron, because of repolarization, it can't like go backwards and then go again back and forth and back and forth. You get this crazy feedback in your neurons. Then number 4, the sodium-potassium exchange pump pumps out the sodium and then pumps in the potassium rapidly. So all that sodium that flushed in during depolarization then gets pumped out to get the cell back to resting state, back to polarization state. All that potassium that flowed out during repolarization to stop the signal then gets pumped back in rapidly. So it takes potassium now in, sodium out. And it does it really fast. An action potential in part of the cell membrane will cause the adjacent part to depolarize. Have you guys ever played dominoes before? Actually, not the game dominoes, but taking dominoes and line them up next to each other and then like have a long row of dominoes, then click one of the dominoes over on top of the other. And it goes, and one domino hits the other domino, hits the other domino, hits the other domino, hits the other domino. That is how the neuron functions. That's how an action potential travels down a neuron. You get depolarization, repolarization in one location. That's one domino falling over. That domino hits the next domino and causes depolarization, then repolarization, depolarization, then repolarization. The next one hits depolarization, repolarization. The only difference is our body's neurons have the ability to put the dominoes back up. That's the job of the sodium-potassium exchange pump. So that given a few milliseconds, if I touch that part of my skin again, I'm going to be able to feel it. So the action potential in part of the cell membrane will basically cause the adjacent part to depolarize. Where is, I could have sworn. And so because the charges are changing, it is just like electricity traveling down a wire. The only difference is instead of our axon having metal inside of it, it has liquid. And instead of using electrons in that metal medium in the wire, we're using sodium and potassium ions. Works just the same, just the same as a wire connecting two electronic devices. And so if you were to look at nervous tissue, you could almost imagine these electrical charges rushing through the dendrites, cell bodies, and axons. And in fact, this action potential doesn't just happen in the axon, it happens in the dendrites, it happens throughout the cell body. The whole neuron is able to travel an impulse from head to toe. And there's lots of ways that these dendrites can be stimulated. Maybe this one will stimulate this one and send the electrical signal, in that direction. Maybe this one will stimulate that one. There's this whole web of connections that makes up our brain, and it's a very complex web of connections. And that is a good place to stop.